Chapter 2 is called the exponential function. So what is exponential? Well, exponential comes from the word exponent. An exponent is just another name for the word index. So index or power. So it stands to reason that we would talk about the index laws. And I've just included index laws there for you. I'm not going to go over those at the moment or go into any detail on them, because for most of you probably know them. You're pretty good at them by now. I've left it until the end of the chapter because really the focus isn't so much just on those rules anymore, but it's more on the derivative. What is the exponential function and how do you differentiate it? So up until now, we've only really had one type of function that we've looked at differentiating, and that is when we've got x to a power. And as you know, you bring the power to the front and you subtract 1 from the power. And with that, you use the product rule and the quotient rule and the chain rule, or function of a function rule, or onion rule. Now, we're moving on to a different type of function. It's going to be called the exponential function. And we need to identify and establish what the actual exponential function is before we start differentiating it. So, you know that you've seen exponential functions, for example, like y equals 2 to the x, or you can put any number there instead of the 2. The important thing is that x is in the index or the exponent, hence exponential. That's where the variable sits, in the exponent position. There are common occurrences of things that behave according to the exponential function, and they're population growth or radioactive decay, etc. So that's why this whole type of function was developed within maths. So just a bit of revision from hopefully you have drawn exponential graphs previously. The graph of y equals 2 to the x is here in blue, and y equals 3 to the x is here in red, and it is the dotted line. So they have quite a similar shape, just like all quadratics, which are graphed to make parabolas, have a similar parabolic shape, a similar U shape. It could be upside down, it could be very skinny, it could be very flat, but basically it is that U shape. So for these exponentials, they all have this nice increasing concave up shape. They have a domain which is all real x, so all x values, all the negatives at x is equal to 0, the graph exists, and for all the positive x values. So the domain is all real x values. However, the range, when it's written in the format y equals a to the x, where everything's nice and positive, the range is all real y values greater than 0. So it doesn't ever get down here to y is 0, which is the x-axis. This graph never ever cuts the x-axis. We say that the negative x-axis is an asymptote for this graph. It gets closer and closer to it, but it never touches it. Now, a really interesting thing about all of these exponential graphs, whether it be y equals 2 to the x or 3 to the x, is the shape of the derivative or the values of the derivative. And what's interesting is that the derivative of, for example, y equals 2 to the x, it's the graph of its derivative is also this similar shape. I'll just get this, I'll just pause this video for a moment and get this demonstration going. So here you can see is the graph in green of y equals 3 to the x, or f of x equals 3 to the x. So it's following that shape that we would expect. Now, you can't actually see this, but I'm going to click on a box that says show the derivative. So the red now is the graph of the derivative. And this is what we're saying is so interesting about these exponential functions. When x is in the exponent or the power, the graph of the derivative is almost exactly the same as the graph of the original function. The gradients at a point are the same value as the y value of the actual function. So I'm just going to move that base value, say to 4.5, and as you get bigger up towards 4.5, 5, the red, which is the derivative function being graphed, the gradient values, it becomes less like the original function. So this is now the graph. The green is now the graph of 5 to the x, and the red is the graph of the derivative of 5 to the x. If I reduce those, so I'm coming back to 4, you can see what's happening. Yeah, the green graph is moving. The red gets closer and closer to it here at around 3-ish, and the moment we go the other side, down below to, for example, a is equal to 2, the derivative has come on the opposite side of the graph, but still has that general same shape. So the way that we write that, or the way that we describe that is, we say when visualizing the first derivative, which is what we saw in the GeoGebra demonstration, we see that a curve very similar to the original graph is obtained. This is not what we found in the past. If you remember, when we had a parabola as the function, the graph of the derivative was a straight line. So that's really they were quite different. The gradient graph was very different to the original graph. Not so with an exponential. So the way that we can write that is we can say that the derivative of a to the x is some constant times these values of a to the x. All that constant does is, well, we saw the effect of the constant back in the demonstration. It either made the values a little bit bigger and the gradient function was to the right of the original function, but then as a increased up around 3, 4, the gradient became less and it jumped to the other side of the function. Now, if you need to see that again, then pause the video, click on the link and play with the GeoGebra demonstration. Now, as you play with that, you'll probably realise that there is an a value somewhere around just a bit less than 3, where the gradient function almost identically lines up. Now, that is the exponential function that we're really interested in, just that particular one. What is that value such that the gradient function is identical to the original function? When we identify that value, we call it E, for it is the ultimate exponential. It is the one that is exact. We use the lowercase letter e to identify that value, and it is approximately this 2.718. So you might like to go back to the GeoGebra demonstration and actually see if you can adjust the value of A and get it as close to this 2.718 as you possibly can. I don't think you'll get it spot on, but you'll actually see the visual representation where the red line and the green line line up. You can hardly see any difference between them. So for the majority of the exponentials, the derivative is almost exactly equal to the function, just out by some factor of k, either bigger or less than. Though, when we get to this value of a being 2.718, we get this situation where the derivative of that number, that 2.718 to the x, is the derivative values are exactly the same as the function values. There's one more interesting thing about that concept. It means that here at x is equal to 0, the actual gradient of the tangent is 1. It's just an interesting fact that only occurs when you've got this special number for your base called e, the exponential, which is this number 2.718.